So hello everyone, this is lecture 14 for the classical physics. In the last lecture we discussed all about the gravitational intensity in all kind of figures and the spheres, and we introduced the gravitational potential term here. So I already told you why we took this negative sign and all these expressions. So today we will see the gravitational potential in different surfaces and at different points. Okay, so for that you need to remember this formula. We already proved this, that potential at any point can be given by this expression. This is the amount of work done by this mass to bring that object from infinity to that point. Okay, so range will be infinity to this distance, so limits will be that, and integration will give you the potential. So let's see. Number one is potential due to a point mass m. So potential due to a point mass m at any point p. So we use the formula. So infinity to r, we put the range. So we already find this intensity for a normal point mass, that is minus gm over r square, so dr. After integrating this you will get gmm over r. When you will put the limits you will find that 1 upon infinity term will come out to be 0, and result value you will get minus gm over rp. So this potential came out to be negative. Okay, so in general if this distance is r, then we put as r, so potential will be minus gm over r. So remember this expression for the potential due to a point mass m at any point r. Okay, now let's see the potential due to a solid or hollow sphere of mass m and radius r at an external point r greater than r. Now it can be a solid sphere or a hollow sphere. There it was a point mass. So what is the potential? So it's just same as we discussed about the gravitational intensity. So we consider whole mass concentrated at the center for the solid and the hollow sphere. Then the gravitational intensity, the formula we will use is this IdR. So I for a solid sphere and hollow sphere is nothing but gm over r square. So it will be minus gm over r square dr. So again after integrating you will get this expression, and on solving that you will get this minus gm over rp. So it's just like same that whole mass is centered at center, and this is just a distance of point p from the center, that is rp. So this will be your potential. So just you need to remember the formula for the intensity, which we already derived for all kind of figures, gravitational intensity. You will substitute here and you will get the value. So this was due to a solid or hollow sphere. Now what will be the potential at the surface of this hollow sphere or the solid sphere? It can be anything. So what will be the potential at surface? So now we will see that we are bringing this any point to the surface. So this will be capital R radius, so infinity to r, so range will be infinity to r and I dr. So I is simple, minus gm over r square. So we will solve it again, and it will give you this expression, minus gm over r. So this will be your potential at the surface due to a solid sphere or a hollow sphere at the surface. This will be your potential. Remember this expression, we will use this. Now potential at an internal point r less than r. Now point is inside this sphere. Okay, and this sphere is hollow sphere or it can be a cell. So what will be the potential at this point? Now see that we have this formula, and this intensity vary in this range, means intensity will be different from here to here and it will be different inside. So that's why we will break these limits into two parts. Means first we will bring the particle from infinity to this surface, then surface to this point. So I will be like infinity to r I dr and minus r to rp. So these are the two ranges I dr. Now I for this range, we know this value is same as gm over r square. We already used this was our intensity in this range, and we already proved that for a hollow sphere or a cell inside gravitational intensity is 0. So we will put 0 here, so this term will be 0, and after solving it you will get this expression minus gm over r inside. So this potential is same as what we already derived at the surface. So this potential will remain same. It's like a same as you see in the electrical properties also, means inside the potential remains same as it is on the surface. So it's just the same, means potential inside will remain same as it is on the surface, minus gm over r. So this is very important result, remember this. In case of hollow sphere or spherical cell, potential remains same everywhere inside a sphere. Okay. Now fifth point is, now we will take this sphere as solid sphere. Means now it's not a hollow sphere or cell, it's a solid sphere. So potential at an internal point of a solid sphere R less than R. So we again break the limits to two ranges, means the I out and the I inside, to bring the point inside or the particle inside. So I inside will be minus gm over r cube r. So inside a solid sphere, gravitational intensity at point r, we already derived this expression in the gravitational intensity, that minus gm over r cube r. This is the radius of whole sphere and r is the radius of that sphere up to which we are trying to finding the gravitational intensity. So this was our formula, and I out is same, minus gm over r square, as mass is concentrated at the center. So these values we have, and total potential at P will be infinity to R. So we'll divide this range, infinity to the surface R, then R to small r. So we'll substitute these values here. I out will be this, minus gm over r square, and I inside is minus gm over r cube r dr. Now just integrate these. 1 upon r square will give you this. So this is our potential, and after solving this you will get this expression. It's the simple math. So we'll take the minus gm over 2r cube common. So it will give you 2r square minus r square plus r square. So this will give you 3r square minus r square. So now we have the expression for the potential. Vp will be minus gm over 2r cube 3r square minus r square. So this is the potential at any point inside a solid sphere. Okay. Now you can from here find the potential at the center also. Means when r equal to 0, then potential at the center of the solid sphere will be minus 3 by 2 gm over r, because this will be 0, this will give you single r here. So this will be your value. Now see, if you put r equal to r here, then you will get again the expression for the potential at surface, minus gm over r. Now we discussed all about the potential. Now let's see about the potential energy now. So potential was to bring a unit mass from infinity to a point. So per unit mass, the work done gives you potential. So this was your expression. From here you can see that potential multiply this mass will give you the work done, and work done is negative. So potential energy is negative in this area. So we can describe this thing as see, this is a attractive force between them. So we will get a negative potential. Definitely, I already told you why. Because gravitational intensity is negative. So you can just see that to bring any point from here to here, you are not doing any work from outside. You are not putting any external force. This whole work is done by this sphere or this mass. So that's why the work done by the system is always negative. Okay. So, and because you are moving from high potential to low potential, that's why it is also negative. So there are many reasons I can give you why this work done will be negative. Also, this force is okay. So that's why, or you can see that radial direction is in this direction, force is in this direction. So FDR is work done. So this will again give you cos 180 will be minus 1. So negative work done. So that's why it is negative. So I hope you know this. Now in the electrical cases, when there are positive and positive charges, then to bring it in this side, there will be a positive work done, because now work done is done by the source, means by us. So I hope you get this point, that why this work done is negative in this case. And this work done is actually the potential energy. So U is nothing but potential multiply mass m, to bring that mass m. So to bring any unit mass to any point, it is potential. To bring m mass, you will get the potential energy. So this system, to arrange it in this form, means small m is here and its capital M is here. So to arrange the system in this way, there is a need of a energy which binds this. So this is called the potential energy. And this potential energy at this point, how you can find? So potential at this point is minus gm over r. So multiply with small m, you will get the complete potential energy. Now here, what is the reference? We taken the potential energy at infinity is 0, or potential at infinity is 0. So with that respect to, we get this potential energy as minus gmm over r. Now this reference is very important. Let me tell you the importance of this. See, this is Earth's surface, or this is Earth, and we have this point at the surface of the Earth. Now if we need to find a potential at this point, what it will be? Means it's a solid sphere, so total mass will be concentrated here. So this distance is r, so minus g mm over r will be the potential at this surface, and reference is infinity now. Okay, and in the same reference, if we need to find the potential at this point, which is at height h, so this distance will be r plus h, so potential will be minus g mm over r plus h. Now mass of this earth is m and radius is r. Now see, these are the potentials with respect to in the reference of infinity, means the potential at infinity is 0. Now we need to find the potential with respect to this, means what will be the potential of this point with respect to earth's surface. Okay, so how you can find this? So u at q with respect to s, so it will be uq minus us. Okay, so at uq it will be uh, so uh minus us you will get. So potential energy at point q at a height h with respect to earth's surface will be uh minus us. So we'll solve this expression simply, minus this one from this one. After solving we get this expression, g mm h over r square 1 plus h over r. From here you can see gm over r square nothing but, this is acceleration due to gravity, small g, so it will be mgh over 1 plus h over r. Now see, this h is very small, means as compared to the radius of the earth. If it is very small, then you will see it will turn out to be mgh. So we are very familiar with this equation, means it is the potential energy at the earth's surface at any point and at any height you will get this expression. So what is the meaning of this? Now the reference is earth's surface, means at earth's surface we consider the potential energy is 0. So with respect to this, at any point if you want to find the potential or potential energy at height h, it will be mgh. So that's how you can change the reference also. Okay, so remember these results, very important. Now there is one more very interesting thing. Okay, it's very intriguing also. See, this is earth's surface and this is our infinity. Okay, so we have this an object here and we throw it, this is earth, mass m, radius r, and we throw this object with velocity v to the upside and we throw it like it goes to infinity. Okay, to infinity, and at infinity it is going to have velocity v1. So we need to just find a relation between them. So what can be the v1 velocity at infinity? Okay, when potential was 0, at infinity we know that this is 0, and here we throw it with respect to with speed v. So the relation between these, so see, it is a central force system, so its potential energy will be, means its total mechanical energy will be constant, because we know gravitation force is central force, it's a conservative force, and k plus u will conserve. So kinetic plus potential at this point will be equal to kinetic plus potential at this point. So at this point will be half mv square, and potential at this point is nothing but minus g mm over r, will be equal to, at this point potential energy is 0, so it will be half mv1 square only. So see, this relation is very helpful. You can find the anything if it is not given any variable, so you can find the other variable using the given ones. So remember this relation. Now see how we can find the escape velocity using this relation. Now see, let's assume we started to decrease this velocity. Okay, this is a constant term. If we started to decrease this velocity, which with we throw this object, then this will start to decrease, because this is constant and this should remain constant. So this difference will starting to decrease, so this will start to decrease, which means v will start to decrease. So we will decrease v up to that point when this whole term tending to 0, means v1 becoming or tending to 0. So at that point the speed will be called the escape velocity, means we throw an object with a speed v, that when it is reaching at infinity, it is almost, its velocity is 0, but it is reaching at infinity. So that velocity from here is called the escape velocity. So let's see, if we put the v1 equal to 0 here, then find this v velocity, that is escape velocity. So put 0 here, so from here you will get m will cancel out and you will get v equal to under root 2 gm over capital R. And you can write this r is r multiply here and multiply here, gm over r square will be small g, so 2rg. So this is called our escape velocity, means with this velocity an object if thrown from the earth's surface, it will go to the infinity and will become 0, means its velocity will becoming 0 at the infinity. So this is called the escape velocity. it is independent of the mass and direction of the position of the body. So it is not depending on the mass of the object, which means whatever, it can be a very big object or very small object, it will remain same for all the objects. And it is approximately 11.2 km per second, because r is Earth's radius and g is constant for Earth. So throw it at any angle, it will need this speed. So let's see one thing. Means in Earth we have the gas molecules, and whether it is molecules or a big object, it will remain same as we discussed, because it is not depending on the mass. So from the kinetic theory, if you have seen my lectures on the thermodynamics, we know Vrms is under root 3 RT over m for the gas molecules. This is the RMS speed in the molecules, means average speed for a molecule moving inside a gas. So in Earth's atmosphere, in Earth's atmosphere, we have Vrms is less than V escape. So if this velocity is less than V escape velocity, then these gas molecules will not leave the Earth's surface or the Earth's atmosphere. So that's why we have gases in the atmosphere, otherwise it will be like moon, no atmosphere at all. So it means gas molecules present in atmosphere has RMS velocity less than VE, that is V escape, on the Earth. So these molecules will not move to infinity due to this reason. Molecules will be trapped in gravitational attraction of Earth and atmospheric surrounding. The Earth will remain intact. Okay, so that's why this life is possible on the Earth, because particles can't leave. But at the moon, there is no atmosphere at moon, because Vrms at there is greater than the escape velocity of moon surface. Means V escape at moon will be different depending on the mass of the moon and the radius of the moon. So that will come out to be less than this Vrms. So that's why there is no atmosphere at the moon surface. So that's all for today. Thank you everyone.